All right. We're good to start. Welcome back, everyone. My name is Pedro dal Castel. I am James student in Indiana University. I'm originally from Brazil. Uh, Hopefully the accent is not too bad. And this is module 3.1, Chemical Fields Diffusion. I want to remind you that this session is being recorded and distributed, live streamed. So no weirdos in the camera except me and James. Okay? If you're less weird than us, please feel free to activate your camera. So in this session, diffusion is something in fields we see that everywhere, everyone is using these words. Gradient, for example, we hear everyone using the word gradient, but what is it, right? What is a gradient and what is a field? Do you guys know? I want to see some questions, some answers in the chat. Jupiter is probably a physicist, so he probably knows, but let's hear from other people. Let's say Avishek, go ahead.
Yeah, so gradient actually registers how a particular quantity changes in the dimensions in the spatial dimension, and the del C del T registers how it changes with time. And when you are taking the Laplacian of that, you are actually taking the dot product of two of the gradients. So yeah. So basically, the right-hand side is second-order partial differential equation in x, y, and z, which registers how the concentration C is changing in time and how the change is changing with time. I mean, in space.
Good, perfect. And Catherine, Catherine said that diffusion is the movement of molecules from high to low concentration areas, which is, I would say density areas, but I think maybe density and concentration are words that we can use interchangeably. So that's absolutely correct. Good answers in the chat. But nobody defined a field, and that's important. What is a field? So before I start that, there is this slide here interrupting me. Learning objectives of this lecture. Understanding the basic idea of a field and a diffusion, and learn how to generate linear and exponential scalar field profiles in CompuCell. We are not going to dive deep in the mathematics, but if you want to do that, you can ask me questions in the Q&A sessions. Okay, so I will present the mathematics because that's important, but you don't need to understand it deeply. We just need the intuition about it, and then you will be able to solve the problems. Every point has a value and a direction. Not necessarily. That's a vector field. Good, Iran. Good to know that people are involved. Yeah, so field is anything that exists in space and time. It's a function of space and time. This is a field in physics, okay? Fields in mathematics have other definitions, but in physics it's something in space and time. So for example, my age is not a field. It doesn't exist, it's not defined in space. If I move to the right, my age doesn't change. So my age is not a field. A field is, for example, temperature is a field, it's a scalar field. The wind velocity is a vector field. It changes in time and it's defined everywhere in space. Scalar fields are the fields represented by one real number. So for example, temperature. Temperature is one real number. For example, 10 Celsius or 10 Fahrenheit or 10 Kelvin. It doesn't have a direction, right? And these kinds of fields are represented by heat maps, isosurfaces, isolines, and curves. There are also the vector fields. So for example, the speed of a fluid is a field because it exists everywhere and it changes in time. And it's represented by literally a field of arrows. So imagine a field like a crop field where all the plants are dancing together. That's more or less a vector field, okay? So you can imagine fields as like a crop field, or for where you have different elevations, a scalar field, or the wind, the movement of the plants as the vector field. In biology, an important scalar field for biology is, for example, concentration of molecules, as mentioned. An important vector field in biology is, for example, cell polarity, cell movement, the cell forces, or the directionality of fibers in a extracellular matrix. And how about a field that is not scalar and not vector? And name one that is relevant to biology. Go ahead, Avishak.
Deformation gradient.
Gradient is a vector field. So I want something that is not a vector field nor a scalar.
The deformation gradient is basically a tensor that maps a point
So that
from
works.
the reference
Yeah.
to the current domain.
Perfect. Yeah. So the deformation tensor is a tensor field relevant to biology. Thank you, Avishak. So from now on, we will stick to the concentration fields because we will address diffusion. And concentration fields, for concentration fields, we use the letter C for concentration. And as a field, it depends on the position, R vector. Okay, so the position is a vector, and time, T. One example of concentration field is growth factors. You can even see it in the lab by using fluorescence. And the more shiny it is, the more intense it is, the fluorescence, the more molecules you have that. So it correlates to the density, to the local density. Stress strain tensor, that's it. The gradient, as mentioned, is the spatial variation of that field. So it generates from the scalar field. If you take the gradient, you acquire this vector field that you can see represented by these arrows, and it points to the direction of most increase of the concentration field. In this little example, you have a valley and a peak. Okay, the peak has value 1, and you can see that the arrows, they point outwards from the valley, and they point inwards at the peak. And the arrows in the middle, they point straight from the valley to the peak. A gradient relevant to biology could be, for example, the potential gradient across membranes in neurons and in muscle cells. Diffusion, as mentioned previously, is the spontaneous process by which matter flows from high to low concentration regions. And we will discuss why that is spontaneous and why and what do you need for diffusion to happen, really. So do you need a fluid to see diffusion? Do you need a fluid or not? Yes or no? Catherine said no. Jupiter said no. No. Perfect. That's right. I'm impressed, guys. Yes, you don't need a fluid. Diffusion can happen in outer space. Do you need interaction between the molecules? For example, do the molecules need to collide or stick to each other or something like this for diffusion to happen? No, no, no. Perfect. Do you need space for diffusion to happen? Yes. Do you need time? You need time. Perfect. Do you need difference in density in different regions of the space? Yes, good. And do you need some kind of motion or thermal energy? Yes, yes, yes. So does some of you have doubts with each specific point here? How is 2 different from 6? Interaction between they are very different. So Kimberly, movement is the let's say the speed, the velocity of a certain particle, and the interaction is, let's say, a force between the particles. Go ahead, Avishek.
Yeah, so what do you mean by difference in density in different regions of space? For example, I can have a space that is kind of like a topological manifold with certain curvature at local points. Diffusion can happen in that region too, with a uniform density. What do you mean by density of what?
I mean density of molecules, and I'm using an Euclidean space, of course, because we are. But if you take, for example, a cell membrane, which is not an usual topology, diffusion can happen there, and but the topology doesn't doesn't change how diffusion works because diffusion is local. So in 2 very close neighboring points, if there is a difference in density there, diffusion will happen.
Okay, well done. Thank you.
Yes, I am saying specifically molecular. So diffusion of molecules, it's written here. All right. So if you have doubts here, please speak. All right, so if you have, this is Kimberly. Take a look at this video here. So in this video, you see that if you follow one particle, if you look at one particle, you see that it doesn't collide with any other particle. It doesn't interact with anything. It just has motion. Diffusion is not air versus glass. So it needs some random motion or your molecules need to displace so that you have diffusion. So yes, you have thermal motion, but it's a very regular motion in glass. But you are correct. And it's not because the area is very dense, it's because it's a solid. Brownian molecular movement to happen. Yes. I mean, no, this is not Brownian movement, right? This is not Brownian movement, and this is diffusion. You have a region with high density and a region with low density. Sharon, I think they can be used interchangeably, but density is more broad than concentration. Concentration assumes you have some sort of molecule or particle. All right, so there is no force here pushing the particles from left to right. They tend to go from left to right because there are more particles in the left and there are less particles in the right. So it's probabilistic. And this is a common misleading example of diffusion. This is not diffusion. When you drop dye in a glass of water and it spreads out, diffusion is not the main process driving the spread out of dye here. So what is the true process that spreads the dye in the cup, in the glass? Convection, Stephen. Okay, so, but What if I leave the glass with water sitting there for many, many hours? Is that going to happen? Or will we see the dye frozen in the glass? Jupiter, no, it's not that. It's actually convection. The motion of the fluid is spreading the dye across the glass. This is not diffusion. So one super cool demonstration of that is from this Brazilian guy called this YouTuber guy. His Manual do Mundo, it's the name. It's a very cool experimental guy. He does cool demonstrations. And in this demonstration, he lets the water in the bottles stay still for like a full day or 2 days. And then he introduces the dye in the bottle. And as you can see, it stays still. It doesn't look diffusing. And he can even shake up and down. It doesn't do anything. It looks frozen. Why? Because diffusion is mostly relevant over short distances. You don't see diffusion happening in real life. You can approximate some processes with diffusion, but it's not actually something we can easily experience in our scale. And when he provokes fluid motion by shaking it in this circular manner, then you can see that the dye spreads fully. So in biology, because diffusion is something that happens over very, very short distances, there is this very cool estimation of oxygen in tissues. So if you go to the web and you ask, what is the diffusion coefficient of oxygen in tissues? Then you can come up with this with this estimation that it takes 5 minutes for the oxygen to penetrate 10 cells deep into a tissue. And it will take 9 hours to penetrate 100 cells deep. So in 9 hours, you cannot see how far the oxygen field diffused. And here I am neglecting consumption, and oxygen will be consumed as it spreads in the tissue. But even if you neglect that, it takes a very, very long time to spread over far distances. Yes, I will show you guys how to make these estimates. So the time it takes for diffusion to happen, sorry, the distance that diffusive field spreads goes with the square root of time. Diffusion in biology is a cheap mode of transport. It can be used for spatial signaling, where cells secrete something that something spreads in space and reach other cells that can sense this material. This is super cheap. And also distribution of nutrients, water, gases, toxins, lipids, carbon dioxide, so on and so forth. Can cells control diffusion? How do cells control diffusion? Answer in the chat. Membranes, channels, good. So in the membrane of the cell, some specific molecules can cross-strate. Other particles require ion channel. Other particles require specific gates through facilitated diffusion. We treat all of them diffusion. Okay, we will not distinguish between these three modes. Okay, we will call all of them diffusion. And this is passive transport because it doesn't require energy to happen. Go ahead, Avishek.
So why doesn't it require energy for happening? Why is it passive again?
It's passive because it just requires difference in density. So in this example here,
Oh,
there
okay,
is
okay,
no energy input. You don't need to push the molecules from one side to the other.
okay. So is
If
it
you
more
want,
like a chemotaxis?
no, the chemotaxis involves forces.
Okay,
So here you don't have force. There's no force pushing the particles from one side to the other. If you want to go opposite to the gradient, if you want to go in favor of the gradient density, which means if you, let's say you are in this stage here, okay, and you want to push the cells from the molecules from right to left, then you need a force. That's
okay,
where those membrane pumps come in, okay? The membrane
okay,
pumps that pump like calcium and potassium and other stuff. Yeah,
okay.
they
Got it.
require energy to overcome the density gradient.
Got it. Thank you.
No problem. Let me take a look at the gradient, a vector field across membrane. Yes, yes, Kimberly, perfect. So the environment also plays a role in diffusion. So free diffusion has one diffusion coefficient. And if there are obstacles, the overall diffusion coefficient will be lower. And if these molecules stick to the objects, even lower diffusion. And let's talk a little bit about the diffusion equation. Why? Because this is ubiquitous. If you read a paper that is working with fields, concentration fields, you'll see this. So it's good to, when you look at it, you see, okay, that's diffusion. So the diffusion equation has a few interesting things going on. So first, C is our concentration. This del by del T is the time derivative, is how the concentration changes in time. And D is the diffusion coefficient. Can I have a pointer? It seems not. Okay. This downwards triangle nabla squared is the second partial time the spatial derivative, sorry, second spatial derivative, which is how the concentration varies in space, but second order, and then concentration again. So when you combine these two terms, this governs diffusion. This is the dynamics behind diffusion. And this is a continuous model. This is a continuous mathematical model. There is also, and you can see it playing out in this very cool video. If you want to get more in depth in the mathematics, understand exactly, is the lower left corner. Yeah, I don't see it, I'm sorry. If you want to see, to explore how these work, and how does this work, and exactly how to solve this, you should see this video here from 3 Blue and Brown, and he runs these beautiful simulations. So in this simulation, what you can see is that you start with very sharp peaks and valleys, and they flatten with time. And you can see, if you are careful, you will see that the sharper the valley and the sharper the peak, the faster they flatten. And as they flatten, they will be slower and slower. They will change slower and slower. This is the continuous model. There is also an agent-based model for diffusion, when you actually have particles and they have some kind of Brownian motion, Brownian fluctuation. In the Galton board, the particles collide with certain obstacles and they have 50% chance to go left and right. And as time goes on, which means as they go down and they collide with these pins, the amplitude of this distribution increases and the distribution flattens. What impacts the diffusion coefficient? I will get to that. Good question. And when you are working with fields in a region, you need to specify how the field interacts with the boundaries. So for example, when the field reaches the boundary, does the boundary blocks the field, or does the boundary say, for example, here the field has to have a certain value, so on and so forth. So the constant derivative 0, let me start with this one in the middle here. The constant derivative equals 0. It means that the boundaries, the borders, act like walls. They do not allow the field to flow outside, and it doesn't allow inflow of material either. So it works like a wall, a solid wall. And if you set a constant value, for example, constant value 0, it means that in all borders of the region, the value of the field is being held at 0. So the field has to diffuse in such a way that it obeys the constraint of the boundary. And there is also this sometimes abstract periodic boundary, which we will use a lot. So it's important to understand. And the periodic boundary condition means that when material crosses one border, it reappears in the opposite border. So this field, which should be like spreading outside like this, it is reappearing the other side of the lattice. Why? How is this useful? So here we are, for example, simulating an infinite space and with regularity. So it's as if this drop-off field was in an infinite space. So it's spreading through an infinite space, but it will eventually touch itself through the other border. So in games, this is used a lot. Things cross one border and reappear in the other. This is exactly what is going on. So it is an infinite space in the sense that you can go to one direction indefinitely, and you will also be moving to the right direction. You will never hit a hard wall. So let's explore how these boundary conditions are useful in modeling, specifically in biological systems. So let's say you have a tumor, and the boundary of your system, of your tumor system, is a blood vessel. And you are simulating the oxygen field. So ideally, the oxygen field comes from the blood vessel and reaches the tumor, which is inside your simulation. So the blood vessel is the boundary. What kind of boundary condition would you use to model the effect of the blood vessel in the oxygen field? Go ahead, Avishek.
So we can include a flux. So we can say, suppose C is the concentration of oxygen, then there's a gradient of C dot N, where N is the normal to the interface between the tumor and the blood vessel to a specific value.
You can do that, and that's a possible solution, but I think that's not biological accurate. Because imagine, Avishek, that the tissue has more oxygen than the blood vessel. In this case, the blood vessel, because you are using a flux, it would still like pump oxygen into the tissue, but this is not realistic. If you have, let's say, the blood vessel has the same oxygen concentration as the tissue, it should remain the same. It shouldn't keep pumping oxygen into the tissue. So I think the most realistic solution here is using a constant value and fix the value at the average concentration, oxygen concentration in the blood.
But isn't that also possible through flux condition where instead of taking the concentration, we take the flux of the difference in the concentrations across the boundary?
Yeah, that works. Perfect. Uh, yeah, the specifics of the tumor don't really matter. What really matters here is that the blood vessel replenishes its oxygen reserves much quicker than the tumor can do anything. So it's as if the concentration of oxygen in the blood vessel is constant. So I would set a constant value in the blood vessel, in the boundary, a positive, a certain value of oxygen field. Let's go to the second case. So atmosphere as boundary to glucose field in an epithelium. So you have the epithelium, you have the cells of the epithelium, they have a glucose field. And now we are simulating our boundary is the atmosphere, the outer atmosphere. Okay, so you have air and epithelium, and in the epithelium, a glucose field. What is the appropriate boundary condition, boundary constraint in this case?
I can think of two things, but I can be wrong. So one
Go
is
ahead.
uh, like zero flux or a constant concentration at the surface of the epithelium. Sorry, yeah, epithelium.
Yeah, so let me try to convince you guys that it is no flux. And if you set the concentration to 0 in the atmosphere, it's wrong. So why is it wrong? Because if you set the concentration to 0, what is going to happen is that our diffusion equation will tell our field to lose material to the border, as if our skin was constantly losing glucose to the atmosphere, which is not what's going on. The atmosphere works as a wall to the glucose field. It does not allow transfer of glucose from outside and inside. But let's say you're modeling a cream, so you're spreading a cream in your skin. And the cream, then I would say, okay, you might use a constant value, then a positive value, a certain positive concentration of glucose. Is that clear? Who did not understand that? Please unmute and let's talk. Okay? Psychotherapy session now. Kimberly, perfect. Yes. So if you have a contact with the atmosphere, it shouldn't transport out. And but there are many like no flux. Yes, Yasmina, no flux. Yes, you can. I mean, if you can make the model as complex as you like, but as a first approximation, I think the no flux is most appropriate because we do not lose glucose to the atmosphere at appreciable levels, or the other way around. We do not gain glucose from the atmosphere at appreciable levels. But you're absolutely right. We can lose one molecule of glucose every, I don't know how many um, picoseconds. Um, all right. So the diffusion solvers in CC3D are the things, the plugins that will solve the diffusion equation for us. So you don't need to worry and to stress out about, oh, how am I going to write to code the diffusion equation? No, Kishore, it's no flux. Diffusion constant for air. Oh, if you're actively modeling the air, you could set a very low diffusion constant. Yes, that's correct. Go ahead, Vishek.
So in the previous slide for the third situation, uh, will it be periodic for the third one? I'm a little confused about the third one.
I skipped the third. You're talking about the third one?
Yeah.
Yes, it's periodic. So let's say
Uh,
we are modeling a small site of tissue, and all the neighboring sites are similar between each other and are similar to the site inside it. So here you would use a periodic boundary condition to model this repetition of patterns in your tissue. So you are trying to model an infinite space, an infinite regularity of that tissue, uh, using just one site in the simulation.
so
Yes,
will there not be also a flux condition along with the periodic? So won't I have two types of boundary conditions?
you can. You can set different types of boundary conditions
Yeah, so
for
I'm
different ones.
thinking of like molecules, because of the signaling is periodic, the molecules can come in and stop. So there is also a flux associated with it.
And the flux will be given by the difference in concentration between
Yeah,
this
yeah,
border on the left and this border on the right.
yeah, yeah. And along with the flux condition, we can also impose a periodic condition because the signaling is periodic in nature,
Yes,
depending on the concentration difference. Is
yes,
that true?
yes.
Okay, okay. Thank you.
Yes, that's how you set a periodic boundary condition. You just say that this point is neighbor to this point, and everything will obey, will work fine. All right. So we have three main diffusion solvers in CompSL. The steady state diffusion solver, appropriate for extremely fast diffusion coefficients. It is expensive though. It's going to make your simulations slower. The diffusion solver FE, on the other hand, is for transient diffusion, where you actually see the process of diffusion happening with time. This is the one we are going to use for all the exercises today. And there is also the reaction diffusion solver, which is very similar to the diffusion solver FE, but it also allows coupling between fields. For example, reaction. This field creates the other field that destroys the other field, etc. Kishore?
Hey, sorry to pull you back, but I'm having a hard time imagining what a periodic condition, boundary condition would look like. Like if you have a concentration gradient to begin with, on one boundary you have a high concentration, the other boundary you have a low concentration, and if you equate this right side boundary to the left side boundary, let's say, then what does that mean?
Look at this image here on the bottom left. This is what it means. The field will spread and cross the border. It will reappear on the other border.
Right, right. But like, how would diffusion work in this case, right? So
Normally, it's the same. It's the same process. You are just saying that this pixel here in the left is neighbor to this pixel in the right.
Mhm.
So for example, you have the piece of lattice here and you have the drop of dye here. Now imagine a repetition of the same block over and over, left and right. Okay. Now forget the periodic boundary. Now imagine that this is your system. Your system is an infinite repetition of these configurations here. Okay. What is
Right.
going to happen? The diffusion will happen normally. There's nothing wrong here. As they spread, they will do this, you know. So all of them will do this. So now fixate your eyes in this middle block. So you see one piece of field here, one piece of field here and one piece of field here. That's exactly what we see in the bottom left image.
Yeah, but once they start to spread and these boundaries collide with each other, would that not create a I don't know, would that not create a contradiction of any
Something
sort?
artificial. It depends. So if your tissue is identical, like all cells are identical in your tissue, you want that because you are in some sense modeling a tissue, a neighboring tissue that is behaving the same way as yours. But you are right. If you have, for example, imagine you have one cell growing in a periodic boundary condition and then it touches itself. It doesn't make sense, but you're absolutely right.
Okay, yeah.
It can be weird. You can reach some let's say nonsense out of this, definitely.
But given the context, it does work out. Thank you.
All right. So these are the three types of diffusion solver. And as I saw in the chat, transient is when you care about how the things change in time. In a capillary, Sharon, yeah, Sharon is absolutely right. And there's also in how do you call that cell that wraps around the neuron? That's also touching itself, isn't it? Schwann. Yeah. Yeah, biology can be weird sometimes. Okay, so now let's take some time and do this. So you open your wizard and find when you set up your simulation, you will find this simulation, this window in the wizard called chemical field diffusers. So take your time, create a simulation, put some cells there, and give it a name, and reach the chemical fields window. I will follow along. So CC3D project, new CC3D project, or Ctrl-Shift-N. You should be familiar with this. If you are not, please ask the TAs, go to a breakout room, and they can help you. So Python plus XML next. Next, I will create two cells, cell A, cell B, it doesn't really matter. And so now we reach this window here called chemical fields. And I will now launch the poll to see how you guys are with this exercise step here. So I just want you guys to reach this window. And this window has four components. So the first component is this field name field, this blank field where you type the name of your field, for example, oxygen. Second, you have the solver. So in the solver, you have some like the diffusion solver, you have the steady state, which we discussed, and you don't have the reaction diffusion solver because that's set manually. And you have other ones, but they are outdated. So you will like 99.9% of the time choose diffusion solver FE. And then you hit add. So when you hit add, your field with the specific name you set and the specific diffusion solver will appear in the list. So please do that, and I will launch the poll to see if you guys successfully reach this part. reaction diffusion system later. Jupyter. No, but if you want, you can do your hackathon in it, and we will provide close help. Yasmina, multiple calls of diffusion solvers. Let's say you are modeling, for example, diffusion of viruses and diffusion of oxygen. So a virus is a large cluster of molecules. It diffuses much slower than oxygen. And if you want to see both happening at the same time, maybe you would use the steady state diffusion solver for oxygen and the diffusion solver for viruses. But this is a very unlikely situation. I've never seen someone using multiple solvers at the same time. Okay. Let me skip this. I should have inverted those slides. Okay, next. And then, I don't know, set some properties, whatever, doesn't really matter, and finish. After you finish, open your simulation into Edit, and then go to the XML. In the XML, please go ahead and find the diffusion solver steppables. It is a big chunk of code in your XML. And the title is steppable type diffusion solver FE. Which properties doesn't matter. It doesn't matter, Irin. Just click next and finish. I do not have the simulation, Susan. Can someone take Susan to a breakout room to help her? Or breakout room. Yes, there is a completed version of the simulation she can open, and it's on student materials demo. It's called I don't remember what it's called. It's the only simulation that has the word expo for exponential, or like diffusive something field, whatever. The one that is not ecosystem in the demos. Okay, so find the steppables and look at it. Okay, that's the exercise. So I will relaunch the poll and see how you guys are on this. Okay, good. So to edit, by default, will predefine lots of these coefficients. For example, there is a value for diffusion constant, there is a value for decay. There are specific values of diffusion and decay specific for specific cells, as you can see. So for example, cell A has a diffusion, specific diffusion, cell A has a specific decay, so on and so forth. So we have to clear some of these stuff first, all right? So after you find your diffusion steppables, find the global diffusion constant and the diffusion constant per cell. So I found mine here, global diffusion constant happens everywhere. And if you set a specific cell-specific diffusion constant, your field will diffuse in a different way inside that cell. And find those. Just find them, don't need to change them, okay? And then the third step, set all the decays to 0. So you see a global decay constant, set that to 0, so 0.0. And there are also cell-specific decay coefficients. and set those to 0, 2. I will relaunch the poll to see how you guys are doing this. Okay, good. I see that most of you, like 98% following. So I will keep going. Next step. Set the secretion to 0. So you should see eventually that there are two secretion lines, cell-specific secretion, okay? Set those to 0 as well. We will cover secretion later. Today, next section, okay, we'll cover secretion. Okay, set all secretion coefficients you have to 0. You can also comment the line by doing Control bar. You can comment the bar and uncomment the bar. Shift bar. Shift. Do you call this bar or slash or what? I don't know. I don't know English.
Maybe hashtag.
Hashtag?
Yeah.
No. No, hashtag is this one.
Yeah.
Yeah,
I
this
thought
is not a comment in, because here we are in XML. If we were in Python, it would be hashtag dash.
dash. Mm.
But dash is this, James, isn't it? I'm talking about this one. This one here. Slash. Okay, that's slash. Thank you. Yeah, so if you go Control slash, you comment a section of code in XML. Good. So let me see how you guys are doing with this exercise. So we will relaunch the poll, and please. All right. So we are good to go. And before I advance, I will go back a little bit and tell you how you can get this chunk of code without starting your simulation from scratch. And this is by using the to-edit code snippets, which we saw yesterday in Pete's presentation. Okay, and I will show you guys once more, specifically here for acquiring a chunk of code in XML. So here you will go to CC3D and just find it. Don't click on anything, okay? No actions. Just hear me out and look out for things, okay? Don't mess it up, okay? So it's CC3D steppables. And here you have the blob initializer, the box watcher, whatever that is, and pif dumper, whatever that is, pif initializer, uniform initializer, and we see our diffusion solvers. So for example, the diffusion solver FE. I will click that, and you don't, okay, don't click that. And here it's asking me if I want to replace the previous chunk of code that I already have, or comment out the code that I have to add a new one. Okay, I will hit cancel, but that's how you can reacquire that piece of code. Yes, Loic, I don't know how to pronounce her name, I'm sorry. So yes, it is correct. Everywhere, on cells, outside of cells, inside of cells, in the borders, everything, okay, in all space. Okay, so let me progress here. Finally, let's go to the boundary condition section. So please find the boundary condition and look at the options. What are global diffusion constant and global decay? So the global diffusion constant is the diffusion constant everywhere, in medium, in cells, everywhere. But if you set a cell-specific diffusion and a cell-specific decay, they will replace the global ones in that specific cell type. Okay, so you find the periodic boundary conditions and look at the options. So here we have constant value. We saw that the constant value can set the parameters here. In mean is the lower border. So like left if you are talking about horizontal, and the bottom one if you are talking vertical. We have the constant derivative, which you can set to 0 to model a hard wall. But here we are interested in the periodic one. So please activate the periodic boundary condition and deactivate the others. So I will do that by using the control / command. So look at me doing it. Okay, pay attention. So here in line 81, I will comment out this section, constant value, and comment out this one by pressing the control / command. And then control / command to uncomment a commented line, in this case, the periodic option. And I will do so also in this line, so control /, and then control / to uncomment the periodic option. So now when I do that, both my X, which means horizontal periodic condition, and my Y, which means vertical periodic conditions, are set to periodic. So that's what you have to do. Please go ahead and do it.
What would be the shortcut on a Mac? I cannot press control and
Mac people, how in Windows I do control /. In Mac is command /. Good, thank you, Mac people.
Oh yeah, thank you.
Nice, good. Okay, Avishek.
Yeah, so why does the periodic condition does not have a similar mean and max?
Because so it's a constraint. Let me open Paint again. It's a constraint. So when you have diffusion, you have one pixel and the other pixel, and then you have the concentration in this pixel and this concentration in this pixel, and then you have flow of matter depending on the differences in concentration. So when you have the periodic boundary condition, what you are doing is basically saying that I should do this actually. You are basically saying that C1 and Cn are neighbors. So you are not setting a specific value here and a specific value here. You are letting them be. You let them be, but they are neighbors. So if matter is flowing and matter is now in C1, C1 will look to the left, and who is in the left? Cn. Cn is in the left.
Okay.
Good.
So what
Could you please say?
do the mean and sorry, go ahead.
Let me just take a look at this question. Could you please say uncomment and comment which one and how? Perfect. So let me go back here to my code and also show the slides. Where is the slides? Here, I lost it. No, here. Okay. So originally, I will repeat the process. So look closely. This is how it was before I made changes. I had a constant value here, and I had a constant derivative. It could be different in yours, okay? Depending on the version, I think this was changed eventually. But I have these ones, and what I do is by pressing Control slash, this command here, Control plus slash, you can also click in the line and go to Edit, and then block comment. And okay, you can also do that. But I'm using the command Control slash. So Control slash to comment these lines and uncomment the periodic line. So comment everything inside the plane block that is not periodic and uncomment the periodic line. So that's exactly what I'm doing.
Excuse me?
Go ahead, Julio.
For the people looking for the shortcuts, you can go in configuration and keyboard shortcuts. You can choose your own shortcut.
Oh,
Maybe if you
nice. Okay.
one of the first ones.
Mm-hmm.
Yes.
Okay, look at this. Okay, I didn't know about that, Julio. Thank you. But what do I know anyways? Clarify the two other boundary types. So the constant value is basically saying that the boundary will always have that same value, the value you set, and the derivative is that it means that the derivative, the spatial derivative of the field in the border will have the value that you set. Okay. I mean the usefulness of them we covered previously in this one. So I'm not going back to that, but in the Q&A session, I can surely go back and review it. I will relaunch the poll to see how you guys are doing this. Good. We have a good sample. So next step is find the initial concentration expression, and this should be commented. It's a line that is originally commented. So I found mine in line 63, and it says initial concentration expression, etc., etc. Go ahead and uncomment it, uncomment the line, and then change the initial expression. So in my case, it's written x times y. What I wanted to do is type in this 100 times, open close parenthesis, x equals, it has to be double equal to 20, and then times y equals 20. And do you know what x equals 20 times y equals 20 does? What does it do, people? Then times 100. What is it doing?
I'm still laughing, sorry.
Perfect. That's it, people. You were absolutely correct. So what does it do, Kimberly?
I'm still looking for the field, actually.
Oh, okay. I was hoping you would say x equals 20 times y equals 20 times 100 is a droplet of field in the position 2020.
But it's just so much better when you say it.
And 0 everywhere else, yes. Or ignore everywhere else. Yes. Yes. It is supposed to be 0 everywhere else by default. Yes. Those are different. Huh, what?
I'm thinking in terms of programming, you're evaluating an expression, and x equal 20 is true or 1 when x does equals 20, and it's 0
Yeah.
everywhere else. So it's actually
Yes.
setting those zeros.
Yeah. Yeah.
Yeah.
Perfect.
default.
Yes. Yeah. Yes. I lose my brain cells as I go like in the lecture, so you should expect me to go crazy sometime. It is setting the zeros. And this statement is either true or false, depending on whether x equals 20 or not, as Sharon is saying. All right. Let me see how you guys are doing with this. So I will relaunch the poll and disturb you again. This poll is so annoying. It's like a slap in your face. You are doing something and the poll appears like suddenly.
You
It's
can just
horrible.
ask people to raise their hand if they need more time, or
Okay.
if they're.
But I'm not criticizing the fact that the poll is a slap in the face. It's actually a compliment. So we should be good to go. Now let's run the simulation. So open in player and run it. And let's hope it, yeah. So I'm seeing this. And go ahead, pause the simulation and change the visualization of the graph to oxygen. So in the graphics window, there is a option to see the cell field, which is usually what we use. And there is an option to see the oxygen field. And this is what I am seeing here. The droplet is in the position 2020 as we set. And I will let it run to see what happens. It is diffusing. And as you can see, it diffuses slower and slower. I will run this again. It starts by diffusing fairly quickly. And as it spreads, it diffuses slower and slower as we discussed before. Perfect. So look at what Omar got. After it diffused for a while, he saw that the material of the field crosses the border and reappears in the other borders. That's exactly what you should expect. If you put the droplet closer to the border, this effect will be stronger. So I will give you guys a little bit of time to explore the boundary conditions. But before that, I will put this droplet very close to the border so you guys can see here the effect of the boundary condition more clearly. So as you can see, there is a little bit of material here in the corner, a little bit of material here in the other corner, and now it starts to appear here in the other corner too. Perfect. So I'm seeing that people are getting the result. Catherine didn't have what's going on, Catherine?
Just nothing. I have a red point, a red dot, and that's it.
Are you running the simulation, or is it like could be paused or
Yes,
something?
Pedro, I'm here the third day.
Can you please see if your global diffusion constant is a positive value?
Global diffusion content. Moment. Instable.
Yes, in the XML, in the .xml, in your diffusion solver block, you should have a global diffusion
Global
constant.
diffusion constant is 0.1.
Ah,
And global decay constant 0.0, as you suggested. And then
okay.
initial concentration 100 times x equals 20 and so on, the funny thing. And then cell type, I only have one cell type actually because I didn't pay attention that we should put two.
That's not a
cell
problem.
Cell 1 is 0.1 and decay coefficient is 0 again, 0.0. And that's all we changed, right?
Yes.
Yeah. Secretion is 0.0.
Okay. So let's try and do something here. So go to make sure you are selecting the oxygen field in your graphics.
Why don't you have her screen share? Let's look at
Yes.
it together.
Okay. Please screen share. Let's take a look.
Yeah. Here you go. That's my screen.
Show us the player. And yes, you have to share your full screen, I think. Hayden, can you send the Google Drive link to people? Okay, let's see the player. Okay. You have the droplet. That's fine.
Yeah, no?
Click play. Let's see. Okay. Okay, there's something weird here going on. I don't know what it is. Do you have any idea, James?
Are you auto scaling the concentrations? Let's see. Can you instead of using can you go to the initial conditions again into the XML? Can we, instead of using this fancy thing, which is hard to understand, just make it 100 times X in the initial condition expression? Can you change just in line 54, make it just 100 times X?
Here?
Yes, please. Okay.
Like this.
That would be fine. Get rid of the times Y equals 20 though. Save that. Save. You always use the save all on the one on the rightmost of the three save options. Okay. Now go back to your player. Let's run it. Stop. Run.
Oh.
Okay. Okay. So now we have concentration. And you are using periodic boundary conditions, supposedly.
I think the periodic boundary conditions are commented out in
Yeah,
line
something is
73 and 80.
What line?
No, it's okay.
it looks all right.
Oh yeah, sorry.
But is that diffusing the
No,
linear field? No.
Not seeing it. Let's see. I'm trying to think whether there's something else happening here.
Is the
There's
global
gotta be-
diffusion set to be
Yes.
something different than 0?
Scroll up.
Yes.
It's over Fe, oxygen. Let's try switching the boundary conditions. I just want to make sure that I have something where I know what was. I mean, I know what the results should be, so let's come back to the back to the simulation for a second. So the simulation is running the diffusion solver because it's creating a new initial condition. And you have periodic boundary conditions. So as we saw, if you have a high value next to a low value, it should change immediately. And it's not doing that. Let's see. It's a little hard for me to see. Can you see the maximum value at the bottom of in the diffusion field itself? It's in tiny print underneath
here?
there on the left. No, on the left.
Ah, here.
That value. Does that value change when you hit run?
No.
No, it doesn't. Okay. So in that case, it looks like it's not actually doing diffusion. Is there other people on a Mac that it's working for?
I stop my screen sharing, yeah?
Thank you.
Yeah.
Are other people on Macs having an issue here?
I'm having an issue, and changing to 100x didn't help. I don't get the stripes even. Just
Wow.
Do you want to screen share it? I mean, I'm just trying to see, is the diffusion solver broken in the Mac, or is it something obvious that I'm missing?
Yeah.
Both are possible. Usually the
to-
option is that you accidentally pasted the diffusion solver inside of another plugin, but when you do
Oh.
that, it would not display the initial conditions.
Yeah, it should break completely.
Sharon, do you want to screen share?
I'm actually running it on a different computer than I'm running on Zoom, so that would
Okay.
take me to figure out. So I guess no.
Hmm.
Is anybody else on a Mac having an issue?
So what I would suggest for people is download the demo in the Google Drive
See if it
and try
runs.
running that. Try running that. If that doesn't work, because that I'm sure it should work like everywhere, because we could have made a mistake while building the simulation. So if that one there is ready to go and should be fine. If that doesn't run, then I'm worried. So I will keep going. I'm sorry for this. There's nothing I can do in the moment outside directing you guys to the simulation demo. And no file extension. No. What is Hayden? So it should be here. Demonstration fields diffusion. That's the one. You should have access to this folder. I will paste it in. Sorry, I'm not sharing my screen. That's fantastic. So you should have access to this Google Drive, and here you should.
It's 0 bytes.
Yeah, Pedro, you accidentally uploaded an empty file with no extension somehow.
Oh, that's wow. How did that? Ah, I understand what happened. Okay, so oh no. Delete. Move to B. Okay, sorry for that. New file is up. Please download it and extract the files and run. And I will go back to, so this is how my simulation is looking like. So exercise for later, while I'm organizing this mass, is try different boundary conditions and different parameters, different diffusion coefficient, so on and so forth. Now we will build a linear gradient, okay? And the linear gradient should not depend on the initial concentration. So you don't need to change the initial concentration expression. You can leave it being the droplet. But what you need to do is changing the boundary conditions. So as the slide is saying, the change has to be setting the X boundary condition, to constant value. And then, so comment out the periodic line and then uncomment the constant value line. And there you will set 1 and 0 or 0 and 1. It doesn't really matter. And if you do that and leave the other boundary condition to periodic, you should see the formation of a linear gradient in yeah, it's taking a while. So what I'm going to do here is increase my diffusion coefficient by going in the model editor, diffusion, oxygen field, and I will change this to 10.0, for example. So now I see the field spreading, and given enough time, this will eventually generate a linear gradient. A linear field, okay? Constant gradient, linear field. And now it is interacting with the cells, probably because here in my cell-specific diffusion, I didn't set 10. So we'll go ahead and change that to 10 too. So now I can see, oh, this is very cool. I can see the field spreading through some cells and not through others. Well, if I come here and change for the B cell too, then the field will diffuse through all cells as if they were medium. So let me put this to the side. Please take your time to do this exercise. I'll give you 5 minutes. Yes, so the exercise, I will repeat the exercise. The exercise is to set a linear field profile. So this colorful flag all the way from red to blue, or from blue to red, it doesn't matter. Here and you set a high constant value in both sides of your borders. All right, and you do that by changing the boundary conditions. So if you set a periodic boundary condition in the Y and the constant value boundary condition in the X borders, and set different values for those. And so in my case, it's 1 in the left and 0 in the right. If you do that, you should be able to see the formation of a linear gradient.
¿Qué pasa con
It
Tuco?
takes a while.
¿Eh? ¿Qué pasa con Tuco Reci? Tarde, ¿eh?
Ramon Ortiz
yes, sorry.
Catalan. Okay.
Sorry.
Do you have a question? Okay. Ramon, I should say. So I will do the exercise again, just to make sure you guys are following. So I come here to my boundary conditions in the diffusion solver steppables and change the boundary conditions from periodic to constant value, just in the X plane. And then I set different values, for example, 1 in one and 0 in the other. I don't know how Julio managed to do that. Very weird stuff. Is this maybe this is a visualization problem? This shouldn't be happening. Ah, it's intentional. So what did you do exactly? didn't change the initial condition. But I also didn't change the initial condition. And it didn't produce that. Look mine. Look what's going on here.
Pedro, what was a global diffusion constant?
Whatever. It doesn't really matter, the global diffusion, but you can increase it to make the simulation achieve the pattern, the final pattern faster.
Okay.
You can increase to 10, 20, 100.
Okay. I'm not getting what you are getting, Pedro. So I'm getting something very similar to what Julio had.
Why don't you screen share it?
Yeah.
I can do it.
Yasmina, increase your diffusion coefficient a lot to...
Give a value.
What is that? I've
Okay,
never seen that.
let's see.
Can I share screen?
Yes, please.
It says you cannot start screen share while the other
I'll have
participant
to
is
sorry.
unshare.
So I'm getting something like this. Yeah. So in the
Okay, so your values are 0 here, all 0. So let's look at the diffusion solver just finish. And can you go to view and make it bigger so that this text bigger so it's easier to see? Zoom in 2 times.
okay.
Okay. Okay, why don't we just start with something simpler like initial concentration expression is make it just linear gradient. So make it x, just x, just 100 times x. Times x. And get rid of lines 74 and 75. Just delete those. Okay. Comment them.
Yeah.
That's fine. Okay, now you have constant derivative boundary conditions, which is going to create a source. So is that what you wanted to do, Chedra? You wanted a source at the boundary? So make the initial conditions concentration 0 then. Just make
It's
it
just
0.
linear gradient, normal linear
Fine,
gradient.
so you're making it boundary. Okay, fine. Okay. Make that 0.
Okay.
0. And use 0.0, don't use 1. Okay, now scroll down. You have constant x derivative is fine. Okay, yes. Okay, periodic. So that should be all right. Save that. Now run it.
Nothing is happening.
Sorry, let's come back. My mistake. Come back to the code again. I did something silly. We want constant value boundary conditions, not constant derivative boundary conditions.
Yeah.
So where you have in line 81, you need to have constant value instead of constant derivative.
Okay, so
Constant value.
okay.
Look at line 92. Okay, and the same thing for line 82. Okay.
Okay.
Okay, save and run.
Ah, got
Okay,
that.
there.
Yeah, that's correct.
Thank you so much.
In general, I would recommend, unless you use constant derivative 0, which is no flux, I wouldn't recommend using constant derivative boundary conditions unless you have quite a bit of experience.
Okay.
They are useful for certain things, but it represents pouring material in or taking material out of the system. And in particular, if you're taking material out, the values can go negative, which doesn't happen in biologics. So you want to generally, the only safe constant derivative boundary condition is 0.
I see. Oh, thank you.
Sure. And now
Okay,
the Mac people, are the Mac people getting this to work now, or is it still not working?
Well, I've got a weird result. When I did it with the 20 equals x and 20 equals y, I got the initialization, but then it would just go out to 0. But when I simply set with the 20 equals x or the 20 equals y, only one or the other, I get the stripe, and then it works. It diffuses out of the whole field and wraps around.
Probably because I wouldn't use that feature that Pedro was using. I think it's a little risky. So I would use something simpler like the stripe so that you can see more clearly what you've got.
And when I put 100 times x,
Yes.
then I got a high value everywhere. That's
A high value everywhere?
Yeah, I only get a stripe if I say 100 times 20 equals x. But if I say
Okay.
100 times x,
Yes.
I don't get a stripe.
No, well, you're not going to get a stripe. It's going to be a linear gradient.
Well, that's what I mean. Sorry. A
Okay,
field
so
of stripe.
I'm afraid unless you can screen share it, it's hard to debug.
I was about to start zoom on the other one too.
That would be
Oh.
great. Please do. I'd like to help, but if I can't see it from description only, I can't. Now, I do want to know if it's diffusing for people with Macs, because some people seem to have an issue. And so if there's a problem with the Mac solvers, that we need to know.
At least for me, it's working. I made some changes in the code that was downloaded, and now it's working, but from right to left and not from left to right. But
Perfect.
actually, I don't care. Yeah.
Yeah.
Well,
That's
what
it.
was the issue? Did you find the issue?
No, unfortunately not. I don't know.
I'm sorry about that. I'd like to find it for you, but if you've got working code, that's the best. Typically, one problem with XML is it's easy to put in something that clobbers the XML. So if you have a character that's not supposed to be there, or a backslash where it doesn't belong, then the XML, the parser should catch it, but sometimes the parsers miss those things and ignore text. Avishek.
Okay.
So I was wondering I'm sorry.
Go ahead, Avishek. No problem.
Yeah, so in that slide with the graph from C1 to C2, it says constant gradient. So doesn't that mean that in line 81, it should be constant derivative?
In line 81, constant derivative. No,
Instead of
it
constant
will, no, constant value is the constraint in the boundary. It will be a constant derivative as a result of that in the steady state, but the constraint, the actual constraint, is a constant value.
Okay, so line 81 and 82 are like max and min of the concentrations, right?
Yes.
Like a Dirichlet boundary condition.
Yes.
Okay, thank you.
All right, so now what I want you guys to do is in the player, I want you to locate, where is my, this one. I want you to locate these field options. So I'll pause my simulation and go to Tools, Configurations, and then Field. So in this panel, you should see for example, the range of the field. You can, for example, fix the maximum of the scale to 1 or to 100, whatever. Here, because I'm not fixing the maximum will be whatever the maximum is in the field. So here, the maximum is 0.996 because this is the actual maximum of the field in the lattice. You can also set these options specifically for every single field you have. So here we only have oxygen, so these options will apply to the oxygen field, but we could have other options here. And finally, you can set ISO values so that each certain concentration in your field is associated to a line. We are not changing anything here, so keep the settings the same, and let's move forward. So now let's do an exponential field. So here, so far, I have a linear field, which means the gradient is constant. It's the same derivative everywhere. So Kishore, you don't set the derivative, a specific derivative for like different positions in the field. That's a result of the diffusion equation. The dynamics of the field is what is going to dictate how those derivatives will be. But you can draw it if you want. You can draw a field setup and set the diffusion to 0. It will stay that way. All right, so to transform this field into an exponential field, the only thing we need to do is to set a decay greater than 0. So I will go back to my XML and set a global decay constant. So come here and set a global decay constant. You should set to like 0.01 or 0.001, whatever, okay? You can also use this notation 1e minus something, which is 10 to the power of. So by setting a global decay constant, your field will become an exponential field profile. Again, this one is super slow. So what I am going to do for the purpose of demonstrating is increasing a lot the diffusion coefficient for all cells in the model editor. You can do that too. And this field will eventually spread out throughout space, but it's not going to have the same shape of the previous one because of the decay. The decay will make the field go down quickly in the beginning, in the lower end, and so it will decay fast and will not reach the other side. This is an interesting effect here because I didn't set any decay inside the cells. The decay inside the cells is 0. The field is diffusing through the cells. So if I want to have consistency, I can also change here the decay constant to 0.1, 0.1. And we should see this field disappearing now from the cells, and now becoming more isotropic. So Susan, you probably set secretion in your simulation. And now we are very close to the steady state. This is how it looks like when I have decay in the simulation. Go ahead,
Pedro,
Abhishek.
to remind people how to switch between displaying the oxygen field and displaying the cell field.
So to do that, in your graphics window, there is the XY, this layer option, and the oxygen, this drop-down menu where you see the cell field option and the oxygen option. Sometimes it displays like separate from the drop-down, which is weird, but it doesn't matter. And here you can choose to see the cell field like this, or switch back to the oxygen field to see the heat map. So Ali, if you want to put a source line in the middle, you create cells in the middle and then you tell them to secrete. That's how you can create a source in the middle. Yes, I can show my code again. So the only thing I did here was changing the global decay constant to a positive value. Avishek?
Yes, so I just wanted to make sure that I am understanding this correctly. So when you say like you set a diffusion coefficient for cell of type A and B, does it mean how the oxygen is diffusing throughout cells of type A?
Yes.
Okay. And it is not like cell diffusion, it is like
Is the
the
diffusion of the
the
field
constant.
inside the cell pixels. Yes.
Okay, thank you.
I will launch the poll to see how you guys are doing. If you are stuck, please download the demo from Drive.
Instead of doing the poll, why don't you just ask people? Well, right, we've got the poll already.
How are you guys doing with the exercise?
It's good.
Okay. So most of the people managed to solve. People are expecting, but yeah. I just have a few more slides and go ahead.
Yeah, so sorry, I joined late. I was busy with family, but I wanna catch up now. So there is any way that I can watch the video or something to come to the
Yes,
stage?
it's going to be uploaded in YouTube once we
Okay.
terminate the recording.
Yeah, okay, thank you.
Okay, I will have to proceed here. We will help you individually in the breakout room, or please download the demo to catch up. I will proceed with a few more slides before we before we have our break time, because we already because of the problems we had here with player and Mac, unfortunately we had to use a little bit of break time. So this thing we said, the decay, it is a loss of material in space and in time. Okay, so it's basically a loss of material, and the more material you have, the faster it will decay. So the amount lost is proportional to the amount of material. The best example of decay is the radioactive decay. So imagine you have a sample of radioactive material. The more material you have, the faster it will decay, and it has half-lives. Other things that have half-lives are, for example, breakdown of molecules, elimination of drugs from the body, so on and so forth. The diffusion equation is this time derivative of our field minus gamma times the field. So the loss in time, which is minus gamma c, is proportional to the amount of material we have. And gamma, the decay constant, determines the relaxation time, the time it takes for this material to decay. The relaxation time specifically is the time it takes to reach 37% of the initial the initial value of material, and it is intimately related to the half-life. When you couple it to the diffusion equation, simply adding the two terms, it means that the field both spreads in space and also decays, also lose material, going to zero in the long run. The decay, the fact that fields decay, for example, nutrients are consumed by cells, oxygen is consumed by cells, has a big role in biology. So for example, to ensure that all cells in a tissue have access to nutrients, you need capillaries every so often in the tissue, because this field is decaying and it can only reach a certain diffusion length. So when you have decay, the field will penetrate the tissue a certain specific length, and to ensure all cells get access to these nutrients, you need many capillaries at a certain specific distance that is controlled by the diffusion length. Also in tumors, in avascular tumors, you have the inner necrotic core, and the outer healthy layer of cells is determined also by the diffusion length, because the nutrients and the oxygen penetrating the tumor are consumed before they reach the inner cells. And finally, I want to leave you guys with interpretations of the diffusion, okay? And also explain how I interpret diffusion in different contexts. So the basic intuition is that higher diffusion coefficient leads to faster spread. So, and this is determined by the size of the molecule, the viscosity of the medium, and the temperature of the medium, the thermal motion of the particles. So oxygen, a small molecule in water, diffuses faster than protein, a larger molecule in water. A protein in water, in cold water, diffuses slower than a protein in hot water. And also, oxygen in water diffuses much faster than oxygen in cytoplasm, where the medium is more viscous. Also, there is a geometrical interpretation of the diffusion. Imagine your diffusion, your field assumes a Gaussian profile, and then this Gaussian is spreading in time. And the size of this Gaussian, standard deviation of this Gaussian grows with the square root of time. That's how I estimated before that oxygen field will take 5 minutes to reach 10 cells, but 9 hours to reach 100 cells, and not 50 minutes, because it's not directly proportional. It's proportional to the square root of time. And finally, there is the Langevin interpretation, or the Brownian motion interpretation of diffusion, which is, imagine you have a particle, a massive particle, and the medium particles are colliding to that particle, colliding with that particle. And then the diffusion of this particle will be the mean square displacement divided by the time variation. That's it for now. So we have, I think, 10 or 12 minutes of break. So now I will officially open to Q&A, and you guys are free to go grab a sandwich. And also, Ramon, go ahead.
Hello, thank you for the presentation. I had a question regarding, a more specific question regarding the kernel diffusion solver, because I don't quite understand which are the situations where we can use it. I tried in the past with a low kernel range, but it didn't match the same simulation with the normal diffusion solver. So I was wondering if you all just like mention the main highlights of this diffusion solver and the situations that it may be useful to use it.
Perfect.
Thank
Yeah,
you.
so the three main ones are the steady state, the diffusion solver FE, and the reaction diffusion solver. Okay, the standard one is the diffusion solver FE. So most of the time, use that one, the diffusion solver FE. All right, most of the time. If you want a super fast diffusion, which you cannot achieve with your regular diffusion solver FE, then you should consider using the steady state one. But it's a very expensive solver. It takes a long time to run. It will make your simulation very much slower. And the reaction diffusion solver is a very specific situational diffusion solver when your fields interact between each other. Does that answer your question, Ramon?
Yeah, it gives me like an overview of the solvers to use, but I don't know if the kernel one, the kernel diffusion solver, is now. I mean, it's the implementation, because you mentioned that some of them are
deprecated.
Not, yeah. I don't know if this one is still like useful in the newest version of Compusel.
It's
because
deprecated.
The problem is I have like a okay. So I
the diffusion solver FE is more optimized than the kernel.
Okay. Okay, perfect. Thank you.
But they do essentially the same thing.
Okay, thank you very much.
Please fill out the poll. It's important. And thank you very much for attending. Please go grab a sandwich or something.
What time do you want to start again, Pedro?
Maybe, I don't know, 12:15, 12:30, up to 2.
No, maybe. 12:15. Actually, you better do 12:10 because you're behind by half an hour now. So make it 12:10.
Okay, so 12:10, we start again.
Could I just quickly show what I've got and how it's behaving?
I can screen share now.
Yeah, let me
Seem
stop
to be quite
this.
a few questions, Pedro, so we better try to work through.
Okay, all right.
You see my screen? Are you
Yes.
seeing my screen? Yes. So I'm sure I have the parameters wrong. So
Can
this
you
was
make
your
the font, can you make the font bigger, please?
maybe. How do I do that?
Well, it'll be Control Plus on a Windows machine. There's a
Command
you
plus.
have a
Yeah, that doesn't seem to be
under
doing it.
View, go to View,
Hmm.
zoom in.
Shift Command equals. Shift Command equal. No, it's not
Does that
doing
not
it.
work? All right. Well, if it doesn't work, it doesn't work. Okay, never mind. It's all right. Okay, so what
All
is the
Okay, if you can see this highlighted here, right here,
Yes.
that was the original formula.
Yeah.
Actually, I think I'm running the other one. Let me run this one. Open in player. Okay. Nope. Stop. What's going on here? Oh, that's the wrong one. This one, open in player. Okay. I start from the beginning. I've got my little point.
Yeah.
And when I play it, it starts to work, but then it fades out to 0. Like
That's correct.
That's correct. I thought it was
Yes.
supposed to spread out, but that's not. It's not how Pedro's looked. It would.
Okay,
stay
let's look
right
at
in
the parameters you got.
No, it's exactly that's correct. The only difference is that in mine, I unfixed the maximum of the field.
Wait, I thought. Do you mean?
In the display, you have
Yeah.
fixed value. So the maximum value will go to 0 because the chemical will diffuse and the total amount of chemical is very small.
Okay. Was that the thing in here?
Yes.
Yes. Uncheck the fixed on the box. To have floating display, auto scaling display. Now hit OK. Now run it again.
Oh. But you didn't do that until quite a bit later.
Look at the value at the top of the color bar.
Yeah.
And you'll see the maximum is going down because you have the spreading of the chemical.
I see. I guess it's been working all along, except it
Yeah.
is strange.
My bad.
Huh.
Okay. Other questions, Susan?
All right.
Could you go over how you changed the field?
Change.
The gradient field so that it's you've got
How do I
two
see?
bars on either side of your diagram. Anyways, I guess I've got my screen here if you
Now that would be good, so we can take a look together.
okay. I'll try sharing that. That's what it looks like.
Okay, you're looking at the cell field, so you need to switch to looking at the chemical field.
Okay.
Pull that down and go to oxygen.
Yeah.
Okay, and now you have to hit run again. When you switch the display, you always have to hit run. Okay, good. So you have a constant high value everywhere. Okay. That's fine. Okay, so now let's look at your code.
There's the code. The
And you
code.
actually have where's the in Twidit, where is the simulation that you're running?
I think I know what's going on. Go to edit and go to your XML. But you have to share your entire screen. I think you were only sharing your player.
Right.
Or you have to reshare Twidit.
Okay, just give me a sec. How about I redo that?
Okay, that looks good. Okay, that's the code you're running just now.
Yes. I
down.
do.
Okay.
Okay. Now you have, see, in line 55, you have secretion. You set that to 0.
Okay, I thought I had, but maybe I didn't save it.
Good. Then
You also have the
in
word
your-
constant in line 61, 62, 68, and 69. Those aren't valid expressions.
Here. Oh,
Has to either say constant value or constant derivative or periodic. You can't say just constant.
should it say constant value?
Well, I don't know what you want to do, so you have to tell me.
It was constant derivative.
The only constant derivative you'll ever use is 0. And that means that there's no chemical going in or out of the boundaries. That's like building a wall. If you're in a test tube and there's no chemical flowing in or out of the edge, that would be the equivalent of constant derivative 0.
And also you need to use the uppercase V.
Where? Oh, and
If you
with
look
the
in
value.
in line 72 or line 65, that's the correct syntax. Okay. And let's look at your initial condition. Scroll up. No, you stay in the diffusion solver, but scroll up to the top of the diffusion solver statement. Okay, good. Do you want to have decay here or not? Probably no decay. So set the global decay constant to 0. No, not the diffusion constant, the decay constant to 0. So it has to be 0.0. No, 0.0.
Okay.
Control Z, good thing to remember.
Control Z.
Undo. Control Z.
Okay, thanks.
And there's also under the edit menu an undo function as well. If you forget controls. 0.0. Okay.
Okay, I'm just annoyed with it. So we'll just do this.
Just type 0.0.
0
0.0.
0.
Nothing. 0.0. Good. Save it. Always use the double floppy disk, not the one on the left, the one on the right. The one on the right. You've got 3. There we go. Okay. Now go back to your other player and run. Stop, hit stop and run. Go back. You don't have to reopen it there. Go back to player.
Okay.
Go back to player, switch back to player. There you go. And now hit stop. And now hit run. Okay, there you go. That's working. You said to have a constant value of 1 at the top and the right. And the chemical is diffusing in from the top and the right. You have a constant value of 0 on the bottom and the left. So any chemical that touches there is destroyed. So you have what are called absorbing boundary conditions on the bottom and the right and the left. And you have a source boundary condition, constant source on the top and the right. So that's doing exactly what it should do.
Okay, thank you.
Okay, great.
I don't
So
know. It doesn't look like cells, but maybe I'm taking up a lot of time, so.
So the reason it doesn't look like cells is you didn't define the cell condition, the conditions to make the cell stay cell-like. So when you look at the XML again, if you look at your XML, so you have to scroll up to the definition. You have the cell, scroll up. You have cell type defined. Scroll
Yes.
down. You have the volume set. You have cell volume fixed? No.
Neighbor tractor, center of mass. I don't
So
know.
you didn't fix the cell volume. So you can do this. A simple thing to do for everybody. Put your cursor in line 26. Okay, go up to the CompuCell has Twitted has built in code snippets that help you do a lot of things. Those code snippets for the XML are under CC3D ML at the top and under CC3D Python for Python. If you go to plugins, which is maybe not the most obvious thing in the world, plugins, pull down to plugins and just pull out that. You have a bunch of options here and you want to select volume. Hit volume. Okay. Now hit save. And now do you have the cell contact energy set? I can't see. Did you set the contact energy for the cells?
Oh, no.
Okay, so you're going to do that too. Go to line 28. You can't do it. If you do it inside of another plugin, it'll crash. So you have to do it outside. Sorry, line 29. Line 29. Hit return a few times to give yourself space. And now go back to CC3D ML. Pull down, plugins, contact. Let's see, contact, yes, there we go. Hit that. Okay, fine. Now hit save. So this is what we covered yesterday. I know it takes a lot of practice to get used to it. Now hit save again. Now go back to player. Okay. Hit stop. There you go. See, now your cells are staying there, right?
Yeah, they look more like cells.
Right. So remember, you don't get anything for free. So if you don't say the cells have a volume, they don't have a volume. If you don't say that cells have an energy with a contact medium, they don't. So if you don't set those things, if all you're caring about is the chemical field, then you could ignore the cells. They're not doing anything. But if you want the cells to behave like cells, you have to remember to set those configurations, okay?
All right.
So, okay, I know it's pretty fast, but maybe with that, maybe you can play with that, save that simulation and play with it a little bit and see how things go. Was there another question?
No, this is,
Great. Okay, great. Anybody else before we break?
I had a question.
Go ahead.
Over here we were simulating one chemical field. So if we are taking in account like 2 or 3 chemical field, now
Yes.
each of the chemical field will have their own diffusion length. So due to any secrete or uptake by the cell from each of the 3 chemical field, will we expect any change in the diffusion length at each time steps or each MCS?
Well, you set every field to have its own properties. So you can have oxygen, which diffuses very quickly, that's consumed by the cells. You might have a growth factor that's secreted by the cells and diffuses more slowly. You might have virus that's produced by some cells and taken up by other cells. So you can set any set of combinations of those that you like.
Okay. So if there is a secrete and uptake, so we will see a change in the diffusion length. Like if it's the
No.
necrotic.
Uptake affects diffusion
Yeah.
length. You'll see,
Okay.
if you let Pedro give his next talk, he's going to talk about secretion and
Okay.
uptake.
Okay. And
but-
one more question. Okay. Yeah.
Yes, go ahead.
One more question that we were talking about reaction, that reaction diffusion solver. So over
Yes.
there, is there any constraint like we can use up to how many terms in that particular reaction? Like for glucose, if we are trying to see a chemical field, if there is a VEGF or some oxygen or ATP present, so like how many terms can we use in that particular equation? Like it's like
There's no
only 4.
limit. There's no limit, but it'll be slow if you use a lot.
Okay.
But the functional forms have to be simple algebraic or mathematical functions. You can't define it. There's a limit to how complex the reaction terms can.
Okay, okay. Thank you.
But you could have 10 diffusion fields if you wanted. It would run slow.
Okay, understood.
Okay,
Thank
Abhishek, do you have a last question before we break?
Yeah, one last question. So I'm curious about how the Compusal 3D solves the PD behind the screen. So does it linearize the PD into
No.
kind of like set of linear algebraic equations?
So that's a great question, but I'll have you discuss that separately with Michael in a breakout room if you want.
Okay, great. Thank you.
You can look at the code if you want the numerical solvers. There's this is a finite element solver. There's also a finite volume solver if you want to use that.
Okay, great. Thank you.
TJ is the one who wrote it, so if in the afternoon, why don't you ask TJ about the internals of it, okay? He's going to be talking this afternoon. And he can give you all the details on the code, how the code is written. That's a great question, but it's just, we don't have time to go through that right now. We're a little behind.
Yeah, no problem. No problem.